Good morning, students. Today we'll continue with the chapter complex number, and the topic is Argand plane. What is an Argand plane? So, you have already studied about the Cartesian or XY plane or Z plane, which is used to represent any pair of points graphically. What I mean to say here is that plane which has the x-axis as well as the y-axis. So this one is x-axis, this one is y-axis. The intersection of these two perpendicular lines gives you the origin O. So this one is called as Cartesian or XY plane, and which is used to represent any position or any point graphically. It has two mutually perpendicular axes named as x-axis and y-axis, and the ordered pair, if you remember, it was x and y. So first point will be of x and the second will be of y. So this is Cartesian plane is used to locate any pair of real numbered points. What about the complex numbers? So Argand plane is also the xy plane or the Cartesian plane, but here we consider x-axis as the real axis, that means the real z, and the y-axis as the imaginary axis, which is imz. All right. So and thus Argand plane is used to locate the complex numbers graphically. So looking at this particular graph, one is the real one, another is imaginary. So real is the x-axis points and imaginaries are the y-axis point. So position of this point here, P, gives you a plus iv, where a is the distance on the x-axis, abscissa, and b is of y-axis. And together it is a plus bi. Simply we can write xy also. Okay, and this arg is the argument. Argument is the amount of angle made by the real x, okay, the real x-axis. Any complex number of the form za plus ib can be treated as the ordered pair ab, and accordingly it can be represented on the Argand plane. Example, let's say z equals to 2 plus 3i, how this particular number gets represented on the Cartesian plane. So we have real z as number 2 and imaginary as 3. So distance of any point from the origin is called its modulus. So this distance from origin to point P, this is called as modulus. So the value of modulus, suppose this I am representing as z. So z mod is square root of x squared plus y squared. Here it is a and b, so it will be a squared plus b squared under square root. So 2 plus 3i is nothing but x2 and y3, the real part and the imaginary part. And the way we used to represent any position or any point on the Cartesian plane, in the same manner we represent here for the complex number also. So here the real axis and imaginary axis, look for number 2 on the real axis, it is here, all right. This is the real x-axis and imaginary is 3, so perpendicular drawn from here. So this particular point will give you 2 plus 3i. And the distance, suppose this is p, and distance from the origin to the point is the modulus. So mod z, if z is a real number, z is a complex number. So if the complex number is purely real number, its imaginary part is 0. That is obvious. Okay, so in the Cartesian plane, we have learned in our previous classes, if y becomes 0, then the number is represented on the x-axis. If x becomes 0, the number lies on the y-axis. In the same manner here also, if imaginary part, if it is purely real number we call it, then imaginary part is 0. And the vice versa case, if it is purely imaginary number, then the real part will be 0. So a will be 0 in case of purely imaginary number. Purely located on the real axis, either towards right or towards the left, depending upon the sign of a number. That means if a is a negative number, then it is represented towards the left of the origin. If a is positive number, then it is represented towards the right of the origin. This is of the form a plus I0, or simply you can write a z equals to a plus 0i, both are correct. Okay, this is for purely real numbers. And for pure imaginary, it is z equals to 0 plus ib, where a comes 0. Amplitude of any complex number is the angle made by the complex number on the Argand plane from the positive real axis. That is the numerical value of the angle made by the complex numbers on the Argand plane from the positive real axis. What I mean to say here is, suppose this is one ray, and if I want to rotate this ray anti-clockwise from this point, rotation from this point, like this one rotation, the amount of angle which is made here from the positive real axis, this will give you the amplitude. So the values here, so this becomes theta, and the remaining values will follow depending upon the rotation towards from the positive real axis. So here is one example here, class. Let's revise the Cartesian plane here. The Cartesian plane is divided into 4 sections, which is also called as, so 4 sections. The sections are called as quadrants or quadrant area. The first quadrant, second, third, and fourth quadrant here. Looking at this particular figure very carefully, this particular point will give you the 6, 4, and J4. You can write here 6 plus J4 or I4, you can write both of them, both are correct. So 6 is the real part. If you look at the position of 6 here, perpendicular on the x-axis, and 4 is the imaginary part from here on the y-axis. So 6 plus J4, that is the value of z, the complex number. Similarly here, minus 7 plus J6, minus 7 is the real part towards the left of the origin, 0, 0, and to the down it is minus 2 minus J3. Remember, the first quadrant is the positive quadrant, plus plus, because x-axis is positive and y is also positive. In the second case, x is negative, y is positive. In the third case, both are negatives. In the fourth case, one is positive, another is negative. So we always try to understand this by considering the area. So this particular region is formed by the positive x and the negative y. That's why we write plus and minus. So that's all from today's class. We'll talk about polar representation of complex numbers in the next class. Thank you.